Welcome everyone! Welcome to my Gen4 tutorial series. This is the new version, the 2024 version, which is convenient because Gen4 also has a new version. The previous iteration of this tutorial used version 10, maybe 10.6 if memory serves me, and now we are in version 11.2. So that's why I decided to record a new version of this tutorial. My name is Gustavo Valdivieso. I'm a professor of physics at a federal university in Brazil, and I do these tutorials for my own students, but I publish them on YouTube in the hopes that they can reach a broader audience. And actually, I had an awesome feedback along these last 2 years based on my first tutorial series. People reached out to me and said, "This is awesome, we really needed this, but we don't speak Portuguese," which is my native language. It's the language which I recorded the first version of this tutorial. So I'm putting an effort to do this in English. I hope people can understand me like this. If you have any questions, please leave it on the comments. And I actually already got a lot of questions from you guys. Questions regarding the installation. Some of you had problems installing the Gen4 toolkit, and that's why I decided to cover again a few topics installation-wise. So first of all, let me tell you that everything you see on my slides, I got from their website. I'm not creating anything. I'm just trying to summarize and guide you through the process of learning and writing your own applications. I assume you know the very basics of the C++ language, and I also assume you know nothing about Gen4. That also means, that has a consequence, that is, I'm not going to do advanced stuff in these tutorials. I hope that by learning the basics, you can go and learn by yourself the more advanced features of this toolkit. And regarding the installation, everything I did last time, I did based on their own installation guide, and they have an awesome installation guide, by the way, very detailed. If you had any issues, you should go through their guide. See if I missed anything. I hope I didn't, but based on the questions people asked me, I have a guess about what's going on. So if you go over the previous video number 0, and go over the installation, you would see that we downloaded the source code, or maybe you want to follow a different path and you want to download a binary version for your system. But these are very specific to their systems. If you're using Windows, that works. But unless you're using a specific Linux, I assume you do better if you compile the source like we did last time. Also, we used to have to download the datasets. Now we don't have it anymore. CMake can download those for us. So as long as you have a good internet connection, these should be automatic. I use Linux, and I recommend you do this as well. Even if you're on Windows, you can use a virtual machine, or you can use a Linux subsystem for Windows. But in any case, if you use the same Linux version as I am using right now, which is Ubuntu version 24.04, then you should install these prerequisites. So these are libraries and softwares like the C++ compiler, CMake, etc. Things that you have to download before you are able to build the Gen4. But also, if you want to use the graphical mode, the most modern graphical interface for Gen4, you need Qt5. Now, in the last video, I showed you how to look for these names in your own system, because these change a lot. So if you're using a different version of Ubuntu, or if you're using a different version of Linux altogether, you should follow the instructions that I showed you last time to search for the equivalent libraries on your version of Linux. Actually, if you use a different version of Linux, you're probably going to need to look for different versions of these as well. But if you are any kind of basic user on Linux, you can do this. If you can't, leave me a comment and I can point you to some resources online, or you can just Google it. Now, the installation process is quite simple, actually. We unpack everything, or we already download the unpacked version, use Git on a folder. and then you access that folder and you create two other subfolders, a build and an install folder. The final version is going to be here, and this one is a temporary folder for the compilation. Now you go into the build directory, and we are going to run CMake. You have to point CMake to where the source you just downloaded is. In my case, it's on one directory out and then going into this one. This is the version that I am using, by the way. It's Gen4 version 11.2, patch 2. And then you have to pass a few optionals. You have to set the install prefix. This is where it's going to be installed. Remember, we just created the install folder or directory, whatever you're gonna call it. And we have to say to it that we want to install the data. This actually, in this newest version, you don't have to do this. This is the default. This option is the default one, so you don't have to use this tag. But we want to have enabled the GDML for later. This is a graphical description language that we're going to use later in this tutorial. You also want to enable the OpenGL visualization driver and the Qt driver. Now, this is the point where many people had issues last time, including some of my students. Let me tell you what's going on. If you follow this, you're going to get to the point in my video where we compile one of the examples and we run it. And for me, you can see the detector model in 3D. But for many of you, you just get a black screen. The reason for that is that the Qt libraries, the ones we just downloaded over here, they require you to have a dedicated graphics card. So if you're running on a notebook laptop and you have an integrated graphics card, these libraries are not compatible. I don't know how to solve this, to be honest. If you do, please leave me a comment. I can make another video later telling people how to solve for this. But as far as I understood from the Qt documentation, you have to have a dedicated graphics card to interface with this. The reason is because of their driver. So the graphics card has a driver, a video driver, and the driver communicates with their version of OpenGL. I know this is quite technical, maybe you don't know what OpenGL is, but Qt has its own version of OpenGL, as you can see here in one of these libraries, several of them actually. And this version of OpenGL has issues communicating with integrated graphics cards. How to solve this then? Is this going to make it impossible for you to follow the tutorial? Not at all. You just skip this part, and when you're going to compile, you do not use this tag, the last one. You do not turn on Qt library. So if you did this already, if you compiled and you're having this issue with the black screen, what you should do is you go back to the build folder, you erase everything inside it, have it clean, and then you compile again, but without this option. This will tell Gen4 that you don't want to build the Qt dependencies, the Qt driver, and it's going to fall back into the native X11, the native OpenGL that it is among the libraries that we installed. So you're always going to be able to depend on those, even if you don't have the Qt working for you. Okay, so that's how we solve this. Now, once you execute this, if you get no error messages, you can just make with the number of CPU cores you have available, and when it's done, if you have no errors, you can make install, and that will get you to where we are right now. Okay, moving forward, let's talk about what we're going to do today, because today we are going to write our first simulation. This is going to be a very basic program, but the idea is for me to teach you how to get you from zero to something that works, even though it's not going to do much. Because I understand how it goes. I've been a student myself, of course, and I understand when you get to a new researcher group, your advisor just tells you, look, there's a code that do what we want, but now I want you to change it to make your own dissertation or your own thesis, and you're going to work on your PhD using this. And as a matter of fact, you never even knew the person that wrote that in the first place. And to be honest with you, most of these programs start from one of the Gem4 tutorials, which is fine. This is a fine way of doing this. It's actually how Gem4 instruct people how to do this. But I want to do something different because I'm doing this for my students first. So I'm going to teach them and hopefully teach some of you how to start a Gem4 program from scratch. Maybe that helps teaching you some C++ as well. So what do we use this for, right? I told you last time, but just to be clear, Gem4 helps us simulate particle transport through matter and sensitive detectors. So it's a way for simulating particle physics detectors. It has lots of applications, not only in particle physics, but also in the medical physics area. And we're going to use C++ for this. This is the language which Gem4 is written in. And Gem4 relies heavily on the object-oriented paradigm. What do I mean by that? It's because C++ has several paradigms in it. If you don't know about programming paradigms, you have structured programming, you have functional programming, you have meta-programming, you have object-oriented programming. So you have many paradigms. C++ accepts all of them, and it's up to the programmer to choose to C++ accepts all of them, and it's up to the programmer to pick and choose which one serves him or her best. And in this case, it was already selected for us because it uses, the toolkit itself uses the object-oriented approach, which means we have some classes which need to be instantiated into objects, and also we have some virtual classes which are meant to be inherited by our own classes. We also have static tables and singletons to deal with, because these are manages, and these manage not only instances of running time objects, but also data for us. These manage data for us. So the shortest working simulation needs exactly 4 classes, no more, no less. Everything runs on the run manager. So a run is a analog of an experimental run. You're going to run your experiment, and you can actually have many runs of your experiment, and you have a run manager for that. The run manager needs 3 other classes, and you can see here all Gem4 classes starts with G4, and a few of them starts with VUser just after the G4, so G4 VUser. This means, whenever you see this means that this is a virtual class, which means you have to inherit from it and write your own class. And when we do this, when we inherit from these classes, we have to write a few more things inside of them to make them work. And I'm going to show you how to do this, and we're going to do this together. But first, before we jump into coding, let me give you another advice about how to configure your system for using Gem4. Here I have a terminal, and I'm currently on my home directory. If you want to be sure, you can just cd the tilde sign or $home, and this will make you be sure that you are in the right place. And I'm going to call my editor. I use Visual Studio Code. I'm going to do this like code.bashrc, and this will get you to your configuration file. Again, I'm doing this for Linux, okay? Now go to the end of the file, and you have space to insert a few more lines. You want to add these 2 lines. First one calls your installation, your Gem4 installation. Inside it, there is a bin directory, and inside it, there is a script. And this script sets up the environment for you to be able to use Gem4. Then, you want to export a new environment variable. You can call it whatever you want, but I call it Gem4 include, maybe because it was called like this before years ago, and I just retained the name, but you can actually call it whatever you want. So you export this new variable, and you do like this. You start from whatever you want, and you go into your installation again, but this time it's install include Gem4, because this place is where the includes the C++ header files live. And you need this in order to configure your Visual Studio code. So if you do this correctly, you can go back to the terminal, and if you open a new window, you should see no error message. I'm going to show you what happens if I get something wrong. So I'm going to change one character. For instance, I'm going to remove the H here. So suppose I mess up the directory or the name of the file, right? So I'm going to save this, and I'm going to open a new window, and you're going to get an error message. So if you have no error message, you're fine. Let me restore the original one. I'm going to close again and reopen this. There you go, no error messages. Now, I can close this terminal, and I'm going to open, I can close this, I'm going to open a working folder for myself. So I created this folder, the directory 001 for my first tutorial, and I'm going to start by writing a main program, which is something that we always do in C++, so main.cpp. As you can see, it has nothing at all. And let me take a moment to show you how to write the smallest working C++ program. This is independently of the Jam4. So we always need an int main, and you have to return 0, which tells the operational system that everything is fine with your program. Now we can come here into terminal, new terminal. So if you don't see me coming here with the mouse every time, it's because I'm using the shortcut. Let me hide this. ls shows you your file, and you can call g++ your file, type -o of output, and you can call it tutorial. In Windows, you want to type an extension like exe, but in Linux, it doesn't matter, right? And there you go. This is it. Now there is a tutorial file here, and you can execute it by typing /tutorial. And it does nothing. Of course it does nothing, because there is nothing inside. Okay, now let's dive into the use of Jam4 itself. We need to turn this regular C++ program into a Jam4 program. And in order to do that, the first thing we need to do is to include what I would say it's the main Jam4 library, the run manager. So include g4 run manager.h8. And this squiggly line means that Visual Studio Code has no concept about what this is. It doesn't know what this is, right? And the way to fix this is using that environment variable that we created earlier. So if you hold Ctrl, Shift, and type P on your keyboard, you're going to open the commands palette. Here you have all commands of the Visual Studio Code editor. And for instance, I like to use this. You can type auto save, and the auto save feature is going to appear. I always turn it on. So right now it's off. Yours is probably off as well. Ctrl Shift P, you can turn it on again. So if I change something, you see that it's always saved. I know that because it doesn't have a little dot right by the name. So if I turn it off and I write something, look, there is a dot. It means it's not saved. I prefer it to always save because I make changes and I already compile my changes. Otherwise, I have to remember myself to save it, and it's troublesome. Okay, but again, how do I solve for this squiggly line? You come here and you type UI, and you're going to get this option, Edit Configurations UI. Scroll down and go for the Include Path section. You can copy this one, paste it below, and change the variable for the variable that you created. Mine was g4 include. If you do this correctly, you won't get any error message. If I type it wrong, see, I get an error. So this is a way for you to know that everything is fine. And if you click outside and get no error message, you can just close this window, and now this squiggly line went away, and more than that, if you click here and you type F12 on your keyboard, you're going to be taken into that file. And this is awesome because it will let us do the most important ability you have to develop during this tutorial. It's the ability to learn from the Geom4 original source code. We have to be able to read this and understand what's doing. But not right now. Right now, we need to create our run manager. And this guy is responsible for turning any application into a Geom4 application. And the way to do this is to say auto manager equals new G4 run manager. Okay, and then I have to pass a few options to it, but you know what? Since this is a tutorial and we are starting from scratch, let me teach you a trick. You don't have to create your own manager because creating a manager requires knowledge about how Geom4 works and how your computer memory works and how many cores you have, if it's going to be multi-threaded or not. So actually, Geom4 has the concept of factories. We have several factories which create objects for us. So instead of this, you can come here and say G4 run manager factory colon create run manager, like so. And you can actually pass a few parameters here, but you don't need to. So this is the run manager. This is the guy that now, from this point on, this is officially a Geom4 application. And I can show you that. We just have to do one more thing, which is to delete the manager. Why? Because every time we create an object, we have to delete it. In C++, we say that every time you use the new keyword, you have to use the delete keyword. And inside this, someone is running the new keyword. Okay? Let's see if everything works. Let's compile. Oh, see? Now the editor knows what this is, but the compiler doesn't. G++ doesn't know. So we have to fix that as well. The concept is the same. I have to tell the compiler where the libraries are. And in order to do that, if you have everything configured correctly, you can use this, Geom4 config. You'll see a few options. For instance, if you run with the ---- version, you're going to get the version you're running. And if you run this with the ---- flags, which means compilation flags, you're going to get a bunch of flags. And the last one is this one, -i for includes. And the location on your system of the includes. See, this is the same thing we added to that environment variable for Visual Studio Code. So it's here. I don't want to copy this actually because I'm going to need all of those, not just this one. So the way to do this is to pass this output to the compiler. So let's clear the screen. Go back to our compilation line. And now you type this apostrophe, the one that's backwards. You get two of those. And now Geom4 config ---- libs --- c flags. Let me do this so it's easier to read. So ---- libs ---- c flags. No error message. It's going to compile. And now if you run tutorial, look, this is the proof we have a Geom4 application, because we get this screen telling us the release date, the version, if it's multi-threaded, and a few references for the software and the website. There you go. Now, I want to try to use it, actually. This is just an application. I want to tell Run Manager to start a run. And a run is the analog of an experimental run. Think about when you're at the lab and you want to take data. So you're doing an experimental run. This is an analogy of that. So if I say manager initialize, I'm telling the run manager to initialize my experiment. And this will tell me if I have everything I need or not. So again, we compile and run. And now I get an error. I get an exception, actually. An exception issued during the program start, which makes sense because we just ran initialize. And it's telling us that I have to initialize the geometry. There is no detector construction. So G4 vUser detector construction is not defined. We have to fix that, right? Let's go back here. And we say now, manager set user initialization. And remember, I told you just a few minutes ago that we needed a few classes to initialize the run manager. And one of them is my detector. What I want to do here is create a new detector. So new my detector. But my detector doesn't exist yet. It has to be created by us. It has to be of type G4 vUser detector construction. So I can actually copy this and use it up here. Well, let's organize ourselves a little bit. So we'll include this. We can write to say that this is the manager, and here we're going to have the detector, right? And now I have to create my detector. How do I do this? It's using object orientation. So I have to create a class which will be called my detector. I can copy here. This is the name I gave it. It could be any name. It's going to inherit publicly. So public, and it's going to inherit from this class, detector construction. Now, I open the curly braces and I type a semicolon at the end. Don't forget this one, it's very important. Otherwise, it won't compile. Now, what will I do with this? I still get this wiggly line over there, so it must have something missing, right? Well, if we click here and type F12, we're going to be taken to the definition file. Actually to the declaration file, the header file. And here you can see the class, vUser detector construction. And remember what I said before. Every time you have vUser, it means that this is a virtual class that has to be defined by the user. And you can overwrite any of its members to make it your own, but you have to do it for this one. The ones that has an equal 0, these are mandatory, which means you have to make your own construct method, which has to return a physical volume. This is the volume where your detector is installed. Think of this like it's your lab. It's your laboratory, and you want to construct the lab where your experiment is going to take place. That's it. So what we do, you copy this, everything except the equal 0. You go back, and you paste here. Pay attention. This is under public, so you have to type public here again. There you go. And after that, since we are overriding a method, you have to say override. Why? Because this is an optional keyword from C++. This comes from C++, like virtual, and it's telling the compiler to double check if what I'm going to do here is correct with the prototype of this class. So if I make any mistake and this ends up being different from what's expected, we're going to get an error. Without this keyword, I wouldn't get an error. So I want to get an error if I do something wrong. This is good. Now you can copy everything between virtual and override. Come down here, open the curly braces. You don't need a semicolon here, but you can use it. If you miss it, it's not a problem, but it's come on, just type it always. It's best to overuse it and not get errors than to underuse it and get lots of errors. Okay, so inside here, we need to define the detector geometry. And geometry between codes, like this, because for Geom4, this is more than just geometry itself, the mathematical concept of geometry, because it means, by geometry, it means the geometrical model, so really geometry, like shapes, solids, etc., but also the material model, meaning a description of the materials. This is what we need. So we're going to do this right now, and we can start by the material. So first things first, we need to add here G4 material. And again, I will have to create this material, whatever it is, from scratch, but let's do something different. Let's get a table of materials. So add this one, G4 NIST Manager. And now I can ask this table to create a material for me. So auto, the material I'm going to create is liquid argon, so I'm going to name it LAR. It's because I'm a neutrino physicist and I'm involved with LAR TPCs, and I want my students to be able to create this. So there you go. But I'm going to teach you how to make differently, how to use other materials. So I'm going to call this NIST Manager, and I'm going to call its instance. This means that this material manager is a singleton. And if you're not familiar with this concept in C++ or in any other language, a singleton is an object with a single instance in memory. So you can't copy it. There is only one manager. And that makes sense. You don't want to have many copies of an object that's full of data. And it's just a table. We need to be able to just consult, read this table. So you want to be only one of these in memory. And it's created by the run manager. So instance, find our build material. And now the name, it's G4 LAR, like this. There you go. Now you have a material. And if you want to use a different material, I'm going to show you how. Remember I just said a moment ago how the documentation is really good. So go to the documentation page and scroll down until you find for application developers, that's us. Click on the HTML version and search for NIST. The first result, it's this one, material database. Click on it, and you're going to see all the names of the materials. You have one for each element, but also you have compounds, and here you're going to find not only materials used for particle physics, but also for medical physics, like human tissue, etc. See, there's blood over there. You have skin, you have bones, every material needed, and the description of the material. So you just need to copy one of these strings and paste where we just typed G4 LAR, and you're going to be able to use this material. See, you have even brain. Come on, you can shoot particles into someone's brain. That's awesome. Not for real though, right? This is just a simulation. Okay, so I have a material. Now I need an object, a geometrical description. And for that, I need to include one of the many geometrical options. I'm going to use a box today, so include G4 box. And here we can type auto world box. Why world? Because this is my world, this is my lab. You can call it lab if you want. But Geom4 usually calls this your world. It's the first physical volume. It's a G4 box. You have to type a name. It can be the same one. This is a string, so it can be whatever you want. And then the dimensions in X, Y, and Z. I'm not going to teach you how to use units today, so everything we do uses Geom4 standard units, and for distance, it's millimeters. So 10,000 millimeters means 10 meters, okay? So 10,000 by 10,000 by 10,000, and a semicolon at the end. Okay, so as I said before, geometry plus material gives us what it's called a geometry, and it's called a logical volume. So now I'm going to need another header. I'm going to go back here and include G4 logical volume. So auto logical world. And what a logical volume is the union of the geometrical description and the material description. Right? It also needs a name. So you may copy this name or you can use other name. And there you go. Now, this guy I can use to build anything. And I'm going to build a big box of 10 by 10 by 10 meters. This is my lab. In order to do that, I need to place my detector somewhere. So now I need 2 extra headers. The physical volume, because it's the thing we're going to return at the end, but I also need the PV placements. Now we come here and we say auto physical world equal new GPV placement. Okay, and now this will involve a lot of options. Please pay attention to this. First of all, it asks for a rotation matrix. We have none. We don't have a rotation matrix, so you just type 0. Next is the position. So we want to position this at the origin 0, 0, 0. And now I have to tell what is the thing I'm going to place here with no rotation and at the origin. And this is the logical volume. That's the logical volume. Next, we need a name for it. And I can copy the same name. It's not over yet. The next thing is the mother volume. So when I place objects, I can place objects one inside the other. And I have to pass here a pointer to the object that contains this one. Since this is the first one, it's 0. The last 2 parameters are asking us if this object has more than 1 copy, because I can use this logical volume and I can place multiple copies of it. But this is not the case. I only have 1 world. So false, this doesn't have multiple copies, and 0 meaning this is the number of this copy. It's copy number 0. Type here, false. Okay, that does it. Now we have our lab, our world, and the only thing remaining for us to do is to return the physical world. This is going to be returned through construct, which is going to be part of our detector, my detector, which is going to be passed on to the manager. So now the manager has a detector. Let's compile and see how this goes. We got a linking error. Wow, how do I know this? Because there is an LD back here. This means a linking error. Linking means everything compiled correctly, but there are some functions that can't be linked to any source. And I see my error. It's on my detector, and you can see here that my detector has a construct, right? But I forgot to say that this construct is that construct. It doesn't know this. For all C++ knows, this is a different function, and this one is missing a function. And the way to fix this is to get the name of the class, my detector, paste it here with 2 columns, column. There you go. Let's compile again. There you go, no errors. Let me clean everything and run the tutorial again. And we get another message. Look, now it's different. It's telling us that we have to initialize physics. Okay, let's go back there. It's telling us again that it's missing this guy. It has to be a G4V user physics list. So we're going to copy this because we're going to use it in a moment. So just after the detector, you can type manager set user initialization, okay, and pass on the physics list, which doesn't exist yet. We have to make it. So let's do this. Let's make it. Let's climb up a little bit, just up here, or maybe here, it doesn't matter. We can just say this, the physics list, just so we are organized. So let's include the physics list header. I just copied it from here. But then again, it's hard to create our physics list from scratch. We're going to be using a factory again, so let's call a phys list factory, right? Open space below the manager, so we have to do this after we have a run manager created. And we can start by creating our factory. So auto physics list factory equals new factory. Remember that whenever you have new, you need a delete, because at a certain point I don't need this anymore. I don't need this to occupy space in memory, so I can just dispose of it. And here in the middle, between when I create the factory and I destroy the factory, I will use it to create my physics list. So you can take the same name, physics list, right? And this, I can ask the factory for it. Factory, and then a get reference physics list. There are many physics lists that are ready for us. We're going to be using this one, shielding. It has everything we need. So what do I mean by physics list? This is the part that manages the physics itself, all the physical models. For instance, how my particles are going to interact with the medium, or if they're going to cause ionization or scintillation, right? So all of these physical processes are here in this physics list. Okay, again, let's compile and run. Okay, no error messages this time. See, we have everything we need. These messages come from all the models included in the shielding list, and you can see the energy ranges where each model applies. And the run ends by telling us that it was going to create and start workers, meaning workers are programs that run on your different CPUs. You can have more than one. I have 8 CPUs, for instance. And it started to initialize workers, but it didn't have anything for them to do. We have to come here after the initialize and tell it, tell the manager, to start our particle beam. For instance, I can tell it to shoot 10 particles. And that's going to be interesting, because now we're going to get an error. See? Told you. What's the error? Generate event. It's missing this guy. User primary generator action. This guy is not defined. So remember, we have to define a few things over here, and it's missing one of them. It's missing our particle source. So in set user initialization, we can create a new my action initialization. Again, this guy doesn't exist, and we're going to move up. You can go all the way to the top if you want. Particle source. The first thing we need is this guy. But we also need the same object we were trying to create here, which is the action initialization. So we need both of those, like so. Now we're going to start with the action initialization. So let's create a class. which is this one. It's the one I named. It's going to publicly inherit from the G4 vuser action initialization. Click here, type F12. We're going to be taken to the class, and you can see there are other methods, but the only one that has an equals 0 is the build method. So copy this, everything except the equals 0. Bring back here. Again, pay attention, this is under public. So public. This. Add an override to it. Now copy from here to here. And this time we won't forget to add the name of the class. So it knows that this build is the one that's expected there. And this method build is responsible for building many initializations for our simulation. But today we only need one. Set user action, new, my primary generator. What's a primary generator? Primaries are the particles that they enter your detector. They are the first particles in your detector. It doesn't exist, so I need to make it. That's why we needed these two header files. So come up here, class, my particle generator, and this guy publicly inherits from the primary generator action. Again, click here, type F12, and you see that there is only one method with equals 0. Copy it, go back, public, add an override. Now copy everything between virtual and override. Add the name of the class. And now everything is okay, no more red lines, but inside this we need to create our particle beam. And for that we need some particles. In this example, I am going to use electrons. So we need two header files. The particle gun, which is the particle beam, it's what generates the particles, and what particle I want to be generated. Come back here, and we can create our particle gun. It's a new G4 particle gun. And here we have to specify what particles this gun is going to create. We don't need the particles themselves, only their description. So G4 electron, 2 columns, definition. So this function passes the definition of an electron to the particle gun. Now we have an electron gun, and I tell the electron gun to generate a primary vertex for an event. Let's talk about this for a moment. As you can see here, this function, it needs an event which is passed by the run manager. An event is a particle generation. So for each event, I can generate many particles in the primary, but each event is related to one vertex. Okay? I can actually make more vertices like this. I can create as many as I want, but in general, it's one vertex for each event. And I'm registering a new vertex, so a new primary particle, the source of a particle, into an event, and the run manager is going to create many events with this. Just to be sure that we are doing something, because we're not going to be able to see the results in this simulation. Again, it's a simple simulation. Let's use G4 cout to write to the terminal. And we can write the event ID, for instance. And for that, we take an event and get event ID. And then we end the line. So I want to write on the terminal what is the ID of this event. In order to do this, I need to also call for this library. Usually I don't need to, but if the compiler complains, you can call it here. And we can do the same again. We can ask for the particle name, like this. The particle name is not in the event, it's on the particle gun. You get that particle definition, the one we just passed on, and from that you get the particle name. And just one more, let's ask for the energy, because we didn't define an energy. And when you don't define an energy, the default energy is 1 GeV, 1 giga electron volt. But again, we're not using units today, so if I don't mention the units at all, it's going to come out as MEeV, because MEeV is the standard energy unit of Gen4. So I can say get particle energy, like so, and it's going to write the energy in MEeV. And that's it. If I didn't make any mistake, the simulation is ready. Let's compile and run it once more. There you go. You have event ID from 0 to 9, meaning 10 events. They are all electrons, E- is the particle's name, and with energy 1000 MeV, which means 1 GeV. But if you scroll up, you see there is an exception, which didn't stop the simulation, so this is more of a warning than an exception. And it's telling us that when the run manager was creating the event loop, so to loop over all particles, all events, it was expecting to create at least 3 workers, 3 threads, but it didn't have enough particles to do that, so it created only 1. This means that we are underestimating Gen4. We only asked for 10 particles. I can make this message go away, for instance, by creating 1000 particles or 10,000 particles. Let's do it for 1000. And I'm also going to bring forward this resource viewer, which tells me the load of all the CPUs in my computer. So again, let's compile because of that change and run again. And bring this forward, and you can see that when we start writing particles over there, look, we get all CPUs going into 100%, which means I'm using all the resources my computer have available. This is very important. It can be faster. This is slow yet because the terminal is slow. I'm asking it to run and write here, and if I turn it off, so if I go back to my source code and I turn off writing, of course then I won't be able to see anything happening because this is the smallest simulation, so we don't even have a way to know the results of the simulation. That's going to be done in a future tutorial. But if I turn that off and I run again, you see that last time it took about 10 seconds and now it took a little bit more than 5 seconds. Okay, in order for us to be done for today, let me show you that we can actually not use the compilation line. So what I'm going to do is I'm going to import a CMake lists file from somewhere else. I already changed a few things. I got this from one of the examples that come with Gen4. I just have to change, our main code is called main, so I just have to add it here. And it's going to generate a tutorial executable, just how we did before. And now we make tier builds, we create a temporary directory called build. You go inside it and you CMake ... because we are inside build and we want to CMake the CMake lists file that is outside build. That's why the ... If you get no errors, now you can make. In the same way that we compiled Gen4, we can now compile our code and run it the same way. There you go. You can have this tutorial and all the others if you follow my GitHub. So you have the address. I will leave the address in the description of this video. And right now you have the first one, so you can clone this and keep updating it on every time you see a new video. And the other tutorials are going to appear down below. And here you have the first one, right? So keep an eye for that and let me know if you have any questions. Otherwise, I see you on the next one, where we are going to start exploring the interface between the run manager and the user, which means you. See you then.